Alright, so I'm weirdly obsessed with cluster analysis. So I'm really excited to talk about all the cool details, and I will in future entries to this video series. Today's agenda is simple. We're just going to go over the types of clustering, types of world space, then write an interface for some world spaces, and a clustering algorithm to go along with it. Let's begin! First of all, there are 4 different main categories of clustering algorithms: centroid-based, density-based, hierarchical, and grid-based. Centroid-based clustering defines clusters based on a center point. The bounds of this cluster is defined by a circle spanning out until it collides with the next, which results in cells like this. Each cell is its own cluster, signified here by color. Also, any of these corners are equal distance from all cell centroids it shares a border with. This method is good because of how easily the bounds of a cluster are defined. However, points in concave or hollow shapes, such as this circle, get split into multiple clusters, which is not good. Density-based clustering handles this a little better though. Density-based clusters are defined by densely packed points, and if the points thin out too far, they are no longer considered part of the cluster. An important property to note here is that the centroid might not be near any of the points. For related reasons, it's super challenging to compress this representation. How do you describe this? This method is really good at describing a set of points as contiguous, but it's hard to make any real meaning from it without doing further analysis. It gives especially meaningless data with consistently dense points. Hierarchical clustering splits data into layers of groups. Depending on the implementation, each layer may contain either points like this one, subclusters like this one, or both like this one. This has many implementations, but as a simple example, we can look at quad tree compression. This image is 1920 by 1080 pixels. We're going to sample it down to 1024 by 1024, while maintaining the aspect ratio. Then compress every 4 pixels into 1 pixel, until we have simply the average color of the image. Though we could of course take any layer and call it a new compressed layer. Grid-based clustering splits the space into cells. This is super naive, but it has its uses. Its flaws are glaring though. I mean, look at this. Cyan and magenta are in the same cell, but magenta and yellow, which are closer, are not. Suffice to say, it is not sufficient on its own. Of course, all these methods have their own limitations, but we can make them slightly better by combining them. Like if we added density-based clustering on top of our grid, we get this. Now, typically, we think of points as resting in a Euclidean world space. In a Euclidean space, the distance between 2 points can be calculated using the length of the difference vector. So here we have the points A and B at 1, 2, and 3, 1 respectively. The difference between them is the vector A minus B. Then we can find the length of that vector using good old Pythagorean theorem. Sometimes we aren't in a Euclidean space though. For example, the difference between colors in the HSV cone. Its components are hue, saturation, and value. But we can't find the distance between colors by simply taking the square root of hue squared plus saturation squared plus value squared. As an extreme example, when the saturation is super low, massive swings in hue will have very little effect on the color. But if we raise the saturation, it will have more influence. The HSV cone is still a geometric space though. Then there's metric space. In metric space, points don't have a defined position. The only property of a point is its distance from another. No matter how I rearrange these points, according to metric space, these are all the same shape, because the distance between each connected point is the same. A good real-world example of metric space is roads. Sure, the roads exist in the Euclidean geometric world we're all familiar with. But if you think of yourself traveling between 2 points, you must take the road. The distance between these 2 points cannot be calculated by simply applying a distance formula. Instead, you have to find the shortest path along all the existing roads. Another property of metric space is that the points don't have to be connected at all. There are no roads connecting these 2 points, just like there's no road connecting America to Europe. Now we're going to write some code, starting with an interface for defining metric spaces. This is an interface that takes a point type, t, and contains a method for finding the distance between 2 points of type t. In the future, the distance will return a float, but for today, it will just return a boolean for if the nodes are connected. We're also going to throw in a method for adding connections, for convenience. The graph shape has nodes and a shape defining their relations. For now, we'll simply call these graph shape and node respectively. The node needs a set of connections to other nodes, the ability to add connections, and the ability to check if a node is connected to another. The graph shape is an iMetric space implementation over type node, so it has the methods inherited. We can have add connections forward to node.addConnection bidirectionally and have distance forward to isConnected. Real simple. We can also use a matrix to represent our graph. Here this table has a row and a column for each node in our graph. At each cell, we put either a true or false for if they are connected. Now let's add a connection between nodes A and B and nodes B and C. There is no direct connection between nodes A and C, so we'll leave that false. The cells AA, BB, and CC show self-connections. Self-connections can be useful for some problems, but not for cluster analysis, so we'll just leave those blank. You may also have noticed that this is symmetrical. That is no coincidence. We could simplify it by only storing half the table, but that is out of the scope of this video. To put this in code, we'll make a class named matrix cell and give it an index so we can associate it with a row and column in our matrix. The matrix shape is again an iMetric space implementation, now over type matrix cell with a 2D array as our matrix. Again, we'll need the add connection method. We also need to initialize it with a certain max size, which is a pretty big restriction. It should also be noted that storing values for all unconnected nodes is a waste of memory. Finally, for distance, we can just read the matrix. Both our big issues are resolved by using a sparse matrix. The sparse matrix shape uses a hash set of node pairs in place of a 2D array. This allows for the same easy lookup, but without the size constraints or the unnecessary allocations. So with these implementations done, we can write our first clustering method, connected components. Let's say we have points A, B, C, and D. A is connected to D, and D is connected to C. Therefore, A is transitively connected to C, but B is still unconnected. Connected components would traverse the graph finding all groups of connected points, so A, D, and C would be a cluster, and B would be another. It's that simple. To program it, we'll start with a static class named connected components containing a public static method named cluster. I'm also going to give it a private method, createCluster, and a private refstruct context. Context will contain the properties points, space, cluster IDs, and current cluster ID. Context exists just so we can pass 3 fewer arguments into createCluster. Cluster will create a list of clusters and a context using points and space. Then it will iterate every point in points, and if it does not already belong to a cluster, it will create a cluster around that point by calling createCluster. CreateCluster will start by initializing a cluster containing only that point. Then for every point in this cluster, it will compare it to every other point and add them to the cluster if they are connected. And we're done. To confirm it works, I've written a few test cases using each implementation that we can run. If we run them, you'll see each test passes, and if you want to check them for yourself, it's all on GitHub alongside the rest of my code. You can find the link to the GitHub repo in the description. Thanks for watching. Once again, code is available on GitHub, and after every video is done, I'll make a branch with just the code from that video, so you can always find it. If you like this content and want more, please engage. I have a Discord where you can directly message me with comments, questions, corrections, or ideas. I'd love to hear it all.